So the Rankine cycle is kind of external combustion engine. You can say this is external combustion engine. We'll discuss this later. We can say it is also the vapor power cycles. So why Rankine cycle? We know the Carnot cycle, and it has four different processes for in Carnot cycle. But Carnot cycle, it has some issues, kind of impracticalities. Um, let's say in Carnot cycle, turbine cannot handle steam with high moisture content. So that's one limitations. The other thing is it is not practical to design a compressor that handles two phases. So there are some other impracticalities in Carnot cycle. So all those impracticalities or the limitations that we have in the Carnot cycle, we can eliminate, by separating the steam to the boiler and condensing it completely in the condenser, and that cycle will give us the Rankine cycle. We say this is the vapor cycle. So in Rankine cycle, we have four specific phases. Let's say from 1 to 2, it is isentropic compression. So we have four components here: the pump, boiler, the turbine, and the condenser. You can say this is, if we say this phase 1 or state 1, state 2, state 3, state 4. So 1 to 2, you see, it is the compression. 2 to 3, this is the constant pressure heat addition to the boiler. 3 to 4, it is the isentropic expansion, and the 4 to 1, it is the constant pressure heat rejection in a condenser. So we'll try to understand actually. So here, this is the pump. So we have the water here. So water enters into the pump at state 1, okay, as the liquid, saturated liquid, and it compressed isentropically. If you look here, this TS diagram, you look at, this is the point 1, this is point 2, state 1, state 2. X-axis is the entropy. You see it is vertical, so no entropy change here. So we can say at this section, actually S1 and S2, it is equal. So this is the isentropic process. So we said when the water enters into the pump at state 1, so it compressed isentropically to the operating pressure of the boiler. Okay, so in this case, what we can see, guys, you see this is state 1, this is state 2. So if we say this is actually T1 and this is T2, so that means the water temperature increases slightly, not that much. Because you see the pump, when it enters into the pump, what is happening? The compression. Due to the compression, the specific volume of the water slightly decreased. The specific volume of the water slightly decreased, and the temperature increases. You know this. So it's not that much, it's a slight increase. Okay, so then what will happen? The water enters into the boiler as a compressed liquid, because we already have the compression in the pump. So then water enters into the boiler as a compressed liquid, right? As a compressed liquid. And when it enters into the boiler as a compressed liquid, and it leaves as a, you see the red color, superheated vapor. Okay, at state 3, it leaves as a superheated vapor, because boiler, it is kind of a large heat exchanger, okay, where heat is coming from. Let's say you see the heat in, so maybe combustion gas, other different sources, could be from nuclear reactors. Yeah, so heat is coming here, so it is a large heat exchanger. So the boiler actually, it enters as a compressed liquid and leave as a superheated vapor, okay, at state 3. So now the pressure temperature of this stream drop during this process to the value of state 4. So if you see from state 3 to state 4, okay, so for state 3, you see 2 to 3, it is constant pressure heat addition. And 3 to 4, you can see again we have the isentropic process, and now it is expansion. Previously from 1 to 2 we had the compression, from 3 to 4 it is the expansion. And here you can see we can write here S3 and S4, it is equal, because it is the isentropic processes. So isentropic expansion we can see from process 3 to 4. So the pressure, the temperature, you can see temperature drops a lot. Here the temperature, it is T3, it is T4. So if we go down, that means temperature is decreasing. So here actually temperature 3 is greater than temperature 4, T4. So that means the temperature is decreasing, temperature drop as well the pressure. So then at state 4, you see this steam, it enters into the condenser. It enters into the condenser and then it condenses, and actually it leaves the heat to the, to the surroundings. You can say actually steam, when steam enters into the condenser, in this case it has a high quality steam condensed, and it definitely condensed at constant pressure, which is, it is a large heat exchanger, and it rejects heat. It rejects heat to the surroundings, let's say cooling medium. So it rejects heat, and then what happened, steam leaves the condenser at a saturated liquid, okay, and enters into the pump and complete the cycle. So the cycle, you see how is happening. So at first it is in the pump, then it will be the isentropic compression here, small temperature change due to the low decrease of the specific volume. Then it enters into the boiler as a compressed liquid and leaves as a superheated vapor. Then it enters into the turbine. Then it will be isentropic expansion. Temperature and the pressure drop we will experience here. Then it will enter into the condenser. It will condense at constant pressure, and it will reject heat to the surrounding of the cooling medium, and then it will again come to the pump. So in that way it will complete the cycle. So we need to understand a couple of things here, guys. Look, we actually need the pump in here. Why we need the pump here? So if you look, the pressure at this section A, it is lower than this section 2. So if we want to transport the water from low pressure zone to the high pressure zone, you need some work input. So that's actually the work input we are getting here. You may ask, okay, the isentropic process, why the entropy change is 0 here? If you have this question, so then you see, so initially it is from 1 to 2. Okay, let's try to understand just one by one. So it is from 1 to 2, very small change due to the small the specific volume change. Now when it is in the boiler, then the temperature will increase, the saturation temperature will increase, and it will this is the saturation point, and then the phase change starts from here, and now it becomes the superheated. So at this point it is isentropic expansion. Isentropic expansion, actually we know the entropy change definition, ds, it is equal delta q over, I think, t. You know this definition, right? The delta q over t. So here if you see, guys, what is happening when we are, okay, if I can remember, it is the formula, yes, delta q over t. So actually what is happening here, look, this is the the point 3, this is the point 4, or state 3, state 4. when the temperature, you can see, is changing. Okay, maybe in we'll discuss this one in our next video, otherwise it will increase the length of the video. So I will discuss actually that why this S3 and S4 they're equal here. But we know isentropic means no entropy change. That's the general thing, but we'll try to discuss the physics later on, because if we discuss it then it will increase the length of the video. Anyway, so when then it is some expansion, isentropic expansion from 3 to 4, so we can say it's no change of the entropy. And then again a constant pressure, the it will condense in this condenser with a constant pressure, and then finally it will go to the pump, and it will happen again and again. So now I will quickly try to discuss. You look here, we have a couple of things. The heat in, it is actually in the boiler. Heat out, it is from the condenser. So this is the heat in and heat out. The work is coming to the pump, and it's the work output is going through the